Welcome back, everyone, for the final installment of these Morse lectures. Alessio Figalli will be telling us once again about qualitative stability, geometric and functional inequalities.
Thank you. Okay, so for the last lecture, I would like first to complete the discussion about Brunn-Minkowski, and then I will try to, you can go on with many of the problems, but you can study, stability of minimizers. But I would like to show you also another question, which is a bit different, and I think it's also very interesting, which is about stability of critical points. But before we go there, let me recall where we are. So we were studying Brunn-Minkowski, right? So we have two sets, A and B, of volume 1. Let's have a parameter T between 0 and 1/2. And then I have this functional f of A and B, which is the volume of the semi-sum between A and B minus 1. And the question we want to understand is whether, if this is small, then the two sets have to be at the same time convex and homothetic. So actually the same one up to translation. So I told you that if A and B are convex, then up to translation, you can estimate their difference by a dimensional constant square root of ft over t. So there is a very precise bound that actually is sharp in any sense. So the exponent is sharp, this t is sharp. What if A and B are non-convex? So if A and B are non-convex, you can already consider the case A equal B. And even in dimension 1, this is an interesting question because you are looking at the, let's say, the volume of the, and let me say even t equal 1/2. Right? So you're looking at the A plus A over 2 minus A. So this is your function. And you would like to say that this functional controls how, tells you whether A is close to be convex or not. And so if you look at the example, right, where A is made of two intervals of length 1/2, so this is my A, then this number will be 1 here and 3 over 2 here, because A plus A over 2 will have 3 intervals. So this will be 1/2. But then this set is very far from being convex. And so what Freiman 3K-4 theorem says is that if you specialize it to R, it tells you that in fact this is the only thing that can happen. So if f1/2 of AA is strictly less than 1/2, then the convex sum of A minus A is valuable twice f1/2 of AA. And there are several possible ways to prove it. So there are two actually different proofs. One, for instance, is written. So you can prove it by passing through Freiman's theorem, which is about arithmetic progressions in Z. You can do it by doing a kind of continuous version of Cauchy-Davenport inequality, or you can go directly through Cauchy-Davenport inequality, which is about additive sets in Z3. Just a sketch of proof. So this is contained, for instance, just a remark in my work with Jerison in 2015, something like that. So we just explain how to reproduce this in an elementary way, but there are other approaches. So it would be like, the step is the following. So if you take two sets A and B containing ZP, so Z over PZ, where P is a prime, then the cardinality of A plus B is always at least the minimum between the cardinality of A plus B minus 1 and A. So A plus B is either everything, all ZP, or the let's say if the sets are not big enough that the minimum is this, then it tells you something. So this is called Cauchy-Davenport inequality. And now from this, so this is actually elementary, you can prove it by induction over the cardinality of B. It's not very difficult. Then the second step is that you take now a set in Z, and you want to understand its additive structure. So in general, you have property about the cardinality of this sum with itself, and you want to say that your set has some structure. So in general, so here I will add an assumption that you will not find in standard Feynman theorem, which is to say that, let's say, I can always assume that the minimum point in A is the origin, so 0, so but the origin Z. So I mean that it is 0, 1, 2, and so on. I can always assume that my set starts here, is a finite set, but I'm going to assume that the biggest point in my set is P prime. And with this assumption, it follows that it follows the following. So if cardinality of A plus A minus 2A, so the doubling, how much the cardinality of this differs from the twice the cardinality, is less than A minus 3, then 0 up to P minus A is bounded by A plus A minus 2A plus 1. So if you look at the analogy, you understand why it's called Feynman 3K minus 4 theorems, because 2 plus 1, if you put this on the other side, you get a 3, and here you have a 3, 1 is a 4. So that's the theorem. So this theorem, it tells you that if you have a subset of Z, where the doubling is small enough, how much you increase the cardinality by doing sums of all points with itself, then actually this doubling controls how far you are from being everything. And you see that here is crucial that P is a prime, because if P was not a prime, you could just take any arithmetic progression, and arithmetic progression has extremely small doubling, so you will satisfy this assumption, but arithmetic progression is not full. It has all the gaps that are in the middle. So you could take, I don't know, 0, 2, 4, 6, all the even numbers, I don't know, between 0 and 1,000. And they will satisfy this, but they will not satisfy this. So the trick here is that if you want to prove something on R, R can be discretized by taking just small intervals, and then each interval counts as a point. But you can choose how many intervals you discretize on R, and it's very convenient to take a prime number in your discretization, because then you can kill arithmetic progressions. So that's the trick that simplifies. Otherwise, you have to go to Feynman, where he doesn't put this assumption, and then you have arithmetic progressions around. And so from here, then you just take a limit. I will not do it as P goes to infinity, and you get result in R. So there is a passage to the limit. You see, as P goes to infinity, like you have to think that you are discretizing, I don't know, 0, 1, the interval 0, 1 in points of length 1 over P, and then 0 to P is your interval. Discretization 0, 1. Right. So you have an interval 0, 1, let's say, just discretize it in 1 over P. Something like that. So that's a possible way to prove this theorem. Now, of course, this doesn't tell you much in higher dimension. In higher dimension, you have to come up with better and more complicated arguments. Especially because you see in dimension 1, the convex sum of a set is just an interval. In dimension n, convex sets are a lot, and the space of convex set is non-compact. So convex sets can be very long in one direction, very thin in another direction, so you don't have compact. So even proving, so the theorem that there have been many partial results, but even if you just want to prove that you see F1/2 A tends to 0 implies that the convex sum of A minus A tends to 0, this is not so obvious. So there was a paper by Mike Christ in 2012, and it's not a short proof for it to prove this. You need to extract compactness somewhere. But actually, so over time, there have been many results, and the conclusive one is that actually in every dimension, so so you always need these assumptions, our smallness, and I will say now it's even, but let's say if ft of AA is small enough, then you can quantify it well. Convex L of A minus A is bounded by constant Cn ft AA over A, and written in this full generality. So there was a first result in dimension 2 and 3 by Jerison and myself, and then the general case has been done by Peter, who is here, so Vanito, Spink, and Iba in say 2020. But you have to decide when it's written and when it's published. But maybe published 22. And so this gives the final result when the two sets are the same, right? Because it gives you the sharp one. And now for the general case of Brunn-Minkowski, you cannot, so the idea is that, okay, you want to leverage a bit this proof in some way, but you would like to leverage also somewhere that proof in some way, because you need on the way to fight with two different phenomena. And the general result, I will just state it. For the general case is that if ft of AB is small enough, then you can do the following. You can prove that after translation, A delta B square plus cov A minus A plus cov B minus B. You can write it in a better way, but let me just make it consistent with what I think. Is bounded by constant and then ft. Okay. CFT. If you are okay, there are actually better. I could be more precise. I could also put actually the sharp dependent on t, but then I have to change a bit the powers. But what this theorem is telling you, so this is sorry. So this is myself but into Tiba 23, 24, left. Maybe 20. But what it tells you is that you see you have even for the general Brunn-Minkowski, you have the sharp linear control here and the square root control here. So the Brunn-Minkowski deficit tells you linearly that you're close to each set is close to its convex hull, and with a power 2, it tells you that you are close to the two sets are close, which is exactly which generalizes both this and this.
FT small enough depends on the dimension.
The dimension in T, always on the dimension T. So you can easily see that it has to be at least 2 to the minus n. Sorry, T to the minus n, I would say, because you always take a set and at one point outside and you look how it goes.
And we have T to the n, right?
You have T to the minus n when you combine that with your result, right? Let's say it's not, wasn't written there, then I think we made the remark later, I'm not sure. Yeah, so the later, so in a different paper, Peter and Kevash proved is that you can actually put this really T to the minus n, T to the n, not minus n, T to the n, for the smalls. But then the constant there is not a split. So I don't know, there are bit. So in some cases you can put a square root, but then you lose this power. There are a few things. The theorem is a bit stronger than this. I wrote it in a compact way just to show you what you can do. I don't want to, we spent enough time, and also these proofs are extremely long and technical. Peter gave actually here, when was last semester, a 4 hours presentation of Brunn-Minkowski already. So I don't want to repeat that. So here, the nice part, I think, of what I wanted to show here is that proving the stability results, they involve several techniques which are of different nature. Because, for instance, there is optimal transport for the Isoperimetric inequality, but then, for instance, this kind of approach is very much additive combinatorics. And then you have to combine, for instance, Mike's proof of the qualitative result was based also on harmonic analysis. He used some harmonic analysis technique to prove compactness of the sets. He proved some that if the deficit is small, then you have some kind of fractional derivative, and then you get some compactness. So there are a lot of cool ideas that appear in this kind of proofs. There are many inequalities. You can ask this question for many inequalities, and there has been a lot of work. And I would like maybe now to use a third inequality as a motivation for a different problem. So the next inequality I want to discuss is the two Sobolev inequality. So the Sobolev inequality, I will take the classical one, so you have a dimension n greater or equal than 3. And the Sobolev inequality tells you that if you give me a function u, let's say smooth and compactly supported, it doesn't look very smooth, so this is my u, then the norm, so the integral of u to the power 2 star 1 over 2 star, bound by constant s, Sobolev constant, the integral of the gradient of u squared 1. And where 2 star is an exponent, which is 2n over n minus 2, but okay, it's an exponent. So the Sobolev inequality tells you that if you have a function whose gradient is square integrable, then the function is more than square integrable. It's in a space with an exponent larger than 2. So it is always larger than 2. Okay. Oh wait, sorry. Let me be consistent with my notes. The rest I will put it here. Yeah, here I have to look at my notes a bit. Oh, okay. Let me do it. Sorry. Here I write with this, and now I will rewrite it in a different way. Because this, the normalization constant are a mess. It's not that any of you will check that I normalize correctly, but I wanted to do it correctly. So, let me write it in a compact form. So gradient of u in L2 square is greater or equal than a constant that I put s now, and then norm of u L2 star square. Okay, so you take the squares here, and then I call s the constant that you. Okay, so this is my Sobolev inequality. And the equality case is unknown. So equality, if and only if u is a multiple of a family of solutions which depend on two parameters, lambda and z. So c is a real number. Lambda is a positive number, and z is a vector, is a point in Rn. So, okay, it's normal that, you see, if I have any minimizer, imagine that this function is a minimizer, I can always multiply by c, these two terms doesn't change. So, of course, multiples of a solution are a solution. Now, z is just a translation. So, so u lambda z at x is just taking a function and translating it in z. And then there is a lambda. So, I tell you what it is. There is a dimensional constant. Then you have lambda to the n minus 2 over 2, doesn't matter too much, 1 plus lambda, x minus z squared, and then n minus 2 over 2. So what am I doing? I'm taking a model profile, which is, let's say, u bar of x, which is cn 1 over 1 plus x squared to the n minus 2 over 2. So this is one minimizer. So this function is a minimizer. And then the family of all minimizers is obtained from this one by translating x. So changing the origin. So instead of centering this function, so this function looks like this. Instead of centering the function at the origin, you are centering it at different point z. Okay, this equation is translation invariant. Yeah. Or you could rescale it. So you apply a transformation that rescale the function. And if you do it with this way, the norms don't change. So this transformation in lambda doesn't change neither this quantity nor this quantity. And then you can always multiply by constant. So you have, so the family of all minimizers is obtained by one minimizer plus n plus 2 parameters. So I have one parameter here, one parameter here, and then n parameters here because I have all space of all translations. So this is an n plus 2 dimensional method. Then is an n plus 2 dimensional method. Okay, and now you want to ask, what about stability here? So the stability question actually for this equation, for this problem is one of the easiest one to prove. So if you want a nice, if you just wanted to read one paper about stability of inequalities, I would say the most elementary one is probably this one, because L2 spaces have a nice Hilbert structure. So you live in a vector space, which is a Hilbert structure, you can use a lot of nice things and properties. So actually, so here you could ask, you take your space X, which is the space of all functions. Well, we need to normalize, right? It's always convenient to normalize. I'm going to normalize in this way. So this is the Sobolev constant to the power n. I'm choosing this because these functions have this normalization. So this corresponds to take c equal 1 there. So that's why I have B. And then I have my function f from x into r, where f of u is grad u to square over u and to star square minus s. Some way to write the Sobolev. And now the question is it true that if this is small, I'm close to be one of these? Okay. So the question would be, can it be true that this controls that? So there was a theorem by Bianchi-Egnell in 91, where they proved this result. So this was a problem proposed by Lieb and Bresis and Lieb, where they proved that let's say the minimum or the infimum over all infimum over C lambda and Z of grad U minus C grad U of lambda Z in L2 square is bounded by constant Cn f of U. So they prove the stability with the usual power. Now, here there was an interesting question that has been open for a very long time, which is, do you have any clue how this constant depends on the dimension? So I always ignored until now a bit the dimensional dependence of this constant. But you may ask yourself, can I have any way to understand what this is, what this should be, this constant? What you can always do is to do an approach a la Figalli, which is to say, okay, I have my family of minimizers. So these are my, so this line represents all the functions of the form C u lambda Z. And now my function, let's say, is very, very close to it, somewhere here. And so I could Taylor expand around one of these guys and look how this term behaves when I Taylor expand nearby, a bit as Figalli did. You can do this, and then if you do this extremely close to the manifold, you will get the conjectured number. So you will find a constant that depends on dimension, and you can say, oh, nice constant. I believe this could be the sharp one all the time, which means that, so you can prove easily, right, that there is a constant which is true here, and you would like to say that the constant is actually true everywhere in the whole double space. How you do that? Well, so here there are two problems. You need a way to say that if I have a function u here, how can I relate this expression far away. And then also this neighborhood, if you just do a Taylor expansion, this neighborhood, how close you have to be, this is super exponentially small. Exponentially small in n. So it would be like n to the minus n, the size of the perturbation. Otherwise, you cannot close it with data. So you get a Taylor estimate that you can reabsorb the errors, the little o, but you cannot reabsorb it if you are the epsilon, which measures the closeness. This epsilon will be like this. So you are very close. Epsilon n should be like super exponentially close. So in that way, with this situation, you will never get anything barely optimal in this constant in any way. So anyhow, so you need to develop new techniques. There are competing rearrangement techniques, new kind of analysis that you have to do. But recently, like a year and a half ago, with Dolbo, Esteban, myself, Rupert Frank, and Michael Loss, we managed to get the sharp constant here. So the result with a sharp constant. So just to say that there are results there. I don't want to take that. But okay, so this problem now is essentially understood, but of course it's only for p equal to. But now there is something you could say. You could say the following, okay, let's look again at the abstract problem. What was your, so my lecture started in this way. I have a function f on a space X, and I want to understand the behavior near minima, right? Now, if a point is a minimum, then it's also a critical point, right? So minimizer, so X, let's say a point here, X0. So X0 a minimizer implies X0 critical point. All right. In general, being minimizer and critical points is not the same. So there could be critical points which are not minimizers. But actually, there are many functionals which are non-convex where these two sets coincide. So before that, let me just mention what do you expect in the abstract case. So remember my first example. My first example was the case of Morse functions in array, right? So I said, okay, I have a function f in array now. Let's say that 0 is a minimizer. 0 is the minimizer. And now, so if the Hessian of phi at 0 is equal to is positive, then we discuss that, okay, f of x will behave like x squared at the origin. Near 0. Near 0, right? This was the starting point. This is where you see the power 2 appearing. But now, if you look at critical points, you can say, okay, if I have this, then I can look at the size of the gradient of f. And this by Taylor expansion is equal to the Hessian of f at 0 times x plus little of x. Which means now that the size of the gradient behaves like x itself, power 1. So if you believe in this analogy, if you try to ask the stability, not at the level of energy, but at the level of the gradient, you may expect power 1 to appear instead of power 2. So there is a kind of a difference now between what you expect. And so in this context, in the one of Sobolev, we'll keep probability notation, it's convenient. So in this concept, you could say, okay, let's try to understand the critical points of Sobolev. So what is a critical point? I have an energy, which is f of u, for the Sobolev inequality. Let's see, is there. Okay. So let u be a minimizer of Sobolev. Then what you say, if it's a minimizer, I can write first, let's say, an optimality, criticality condition. So the condition will be a minimal point, a critical point. And now you do this, you say, okay, let's do be a minimizer of Sobolev. Then by minimality, d over the epsilon equals 0 of grad u plus epsilon phi square minus s u plus epsilon phi 2 star square, it should be 0, right? So if you use a minimizer, then it means that this energy is always non-negative, is 0 at epsilon equals 0. So I get 0 derivative. You can do the computation. So you get that this derivative is 0 for every phi, for every test function phi. You do the computation, you discover that minus Laplacian u is equal to a constant, but the constant will be killed because I put myself in x. And then is u to the p, where p is n plus 2 over n minus 2. So you get a PD. All minimizers of the Sobolev inequality satisfy this equation. Here I don't have constants if I assume this normalization. Okay? So that was my reason to set up things correctly, so to get constant 1 here and there. Okay, so here, so this is now my new condition. So before my f of u was this. So now I have a df of u. So df of u is Laplacian u plus u to the p. This is my differential. Right? So this was at the level of the energy, this was my energy. Now the level of differential, this is the differential of my operator. Yeah.
This calculation, how do you know that u is positive to make the transition?
Well, for some minimizers, you know that all minimizers have constant sign.
So it's even known, so it's a minimal.
So I say up to changing u with minus u is always positive. So I didn't say if and only if yet.
Oh, it's not even.
One second. So here I'm just writing the condition of being critical. And so this is the condition of being a critical point, which is of course satisfied by all these minimizers. So all minimizers are critical. Now it turns out, so the f of u is this. Now it turns out theorem, this is a famous theorem in the 70s, there have been more than one proof. So Obata in 72, and then different approach by moving plane by Gidas Nirenberg in 79. But they proved that if I have so Laplacian u plus u to the p equals 0, where u is positive, then u is one of them. So this is a non-trivial result, because this energy that I'm looking at, the Sobolev inequality, is not a convex energy. Okay? So being a minimizer implies being a critical point. But being a critical point should not necessarily imply that you're a minimizer. But turns out that all positive solutions to this PD are actually only the minimizers. Okay, so you have more rigidity. Okay, and now I think I've set up the problem. So this theorem is the 0 case. If my differential is 0, then I am one of these guys. And then the question you can ask would be the following. If question, if Laplacian u plus u to the p is small in some sense, decided, then is u close to U lambda Z. Okay. So this is a nice PDE question, and actually it appears in many problems. Maybe I will mention towards the end some possible application, for instance. And so you ask yourself, okay, can I even opt that? And you think a bit about this. So this is not me. This has been thought since before the 1980s. I mean, it's not. I thought about it now. You think a bit about this kind of question, and it turns out that it's not that obvious because you can do the following. So let me take one of these guys, U bar. I thought it's a nice functional rand. And now you translate it in two different directions. So I take a very large radius, R, sorry, a very large number times P1 and minus area P1. And I'm going to center U bar here. And then I'm going to center the other U bar here. So I consider U to be U bar centered at minus at RE1 plus U bar centered at minus RE1. So you take the sum of two minimizers, just center at a very, very far away point. And now you ask yourself, what can I say about this sum? And now, if you do the operation, so you have minus Laplacian U equal. So let me call this U1 and this U2. So this is minus Laplacian of U1 and minus Laplacian of U2. Now, each of these is a minimizer, so it solves the PD perfectly. So this is U1 to the P plus U2 to the P, which is different from U1 plus U2 to the P, which would be like my U to the P. But the error you make between these two functions is a reminder R, and this is very, very small. So R is a bad notation, because I use that. So it's some error. And this is very, very small, right? Because you see, if these two functions had disjoint support, so one was supported in one ball and one was supported in a different ball, then here I will get equality. These two functions cannot be supported in different domains just because their support is everything. So they're supported in wall array, they're all positive. But the region where they interact, so wherever this lives, this one is extremely small, and vice versa for the other. So it turns out that in fact, so the error here is much smaller than this. It's a perturbation compared to this. Okay, so you can always take minimizer and move them away and get a new one. You could also do a different trick, which would be, I told you that you can rescale minimizers. So you could also take one minimizer again and take the other one, but rescaled extremely high, for instance. Then one minimizer will be supporting an extremely small neighborhood of the origin because it's extremely concentrated. The other one is scale 1. Again, the interaction is extremely small. So this is a phenomenon which is very well known in geometry analysis. It's called bubbling phenomenon. So you cannot prevent bubbling in the sense that you have multiple bubbles. These are called bubbles sometimes. And they kind of go away. So they can be as many as you want, in fact. And these will never be controlled by this quantity. So this is already a bad news. Okay, so the theorem I wanted to prove is just false in this way. And in fact, in the 80s was, okay, maybe there is some replacement for this. And by looking at my examples, you could ask yourself, okay, fine, there is bubbling, but is this the only thing that can happen? So are these the only possible examples? And the answer is yes. This was proved by Mikkel Struve. In 84. He proved exactly this kind of result. He proved that if Laplacian u plus u to the p. Okay, let me be just write a norm, technical norm just for analysts, but otherwise, okay, in h minus 1 is very small. And okay, what else? Here you need a second assumption, right? Because you need, so here I could beat these examples with as many bubbles as I want. So I need to put an assumption to block the number of bubbles I can at most have in my sum. So you write it in the following way. Integral of grad square divided by L plus, let's say, 1/2 s to the 2n. So this is, so each bubble for each u, each of these will carry an integral of this size. So this assumption, where L is an integer, tells you that at most you should have L bubbles. If there are, you cannot put more than L. So this if you build an example like this, you can put at most L of them with such constraint. So if you have this and this, then U can be written as a sum I from 1 to m of U lambda I Zi plus error, where for some m, and the error goes to 0 as this goes to 0, where the number of bubbles is almost L. So there is a, and the theorem of Struve is totally qualitative. So it's an epsilon delta argument. For every epsilon, there is a delta such that if this is less than delta, this will be less than epsilon. So it's compactness. Okay. Okay, so then, motivated by this, one can ask, what if now I want a, quantitative value? So we have been trying for quite a few years. I would say that we started the first attempt more than 10 years ago. And it has been a kind of a long journey here. So the theorem, let me just make sure I don't mess up. So I am in the same situation. I'm going to call now, I have this term, delta u. So let me call maybe delta of u what I want to put in the right-hand side. So this is the norm of Laplacian u plus u to the p h plus 1. So this is like, morally, this is the norm of the gradient of f of u. And then you assume again that the energy then theorem goes as follows. So first case, let's assume again, if you want to prove a theorem, you go by the order of difficulty. Let's assume first that I don't have more than one bubble. So let me assume that L is equal to 1. Okay. So by Struve, I know already that there is at most one bubble. Can I prove a quantitative estimate? Yes, you can prove that then grad u minus grad u lambda z for some lambda z, yeah, is bounded by constant delta u over 1. So your derivative controls the closeness with power 1. So that was what I told you before, right? In the here. We're in this situation, right? The size of the gradient controls the size of the function with power 1. So this would be so here there's a dimensional constant, COS. And this is what we did with Chiraul, myself, and Marci. don't remember, 16 maybe, 17. Okay. Now, what if now L is above 1? So this was a problem that I investigated with Federico Glaudo when he was my student at ETH. Now Federico is here at the AIS. And we proved the following, that grad U minus a finite sum, so up to M of U lambda is a die in R2. So this is the Struve sum, is bounded by Cn delta of U. So this is myself and Glaudo. 2020. Okay. But so some right? But only dimension 3, 4, and 5. Okay. And then in our paper, we built an example in dimension 6, showing that this estimate is just false in higher dimension. So you cannot get power 1 in higher dimension. So we didn't quantify the power, but we showed that the power 1 cannot be 2 in dimension 6 and higher. And then a couple of years later, finally, Deng, Sung, and Wei so L greater or equal than 1. So L greater than 1. Then if any, so you look at grad U again minus the sum of Struve. You want this to bound by something, so you have to do two cases. So if n is 6, then you bound by Cn delta of U, and then you have a square root of log of delta of U. And in dimension 7 and higher, you have delta of U, and then you have n plus 2, 2 and minus. Which
Really mean gradient or minus gradient was.
Sorry?
There's a.
Oh, there's a gradient missing.
yeah. Of course. Sorry, thank you. And the same there. Yeah. It's the closest of the grid. Yeah.
Basically, what's the role of the H minus 1 norm? Like, let's say use the stronger one. The theorem would be looking the same, or?
I mean, it depends. If you just take norm, so you want a norm, the H minus 1 is the natural one because it's the scale invariant one. Is the one which, so you see, U is invariant in H1. The right space for U is H1, so the Laplacian of U is naturally scaling in H minus 1. So this is a quantity which is good in terms of retaking the U, taking your bubbles, rescaling them, and so on. So it has to be translation invariant. And then you would like it to be at least invariant on the transformation of the bubbles. And then either use you have two norms, H minus 1 or the dual of L2 star. These are the two possible norms you can put. It doesn't make a huge difference here. So let's say the theorem is stronger because we put H minus 1, but it doesn't change anything if you put a stronger norm.
But if you put a stronger norm, you don't get in higher dimensions like better results.
No. So, yeah, so it's actually an interesting phenomenon. And this is, again, for geometry, probably is not so surprising. There are many results about on the sphere that change in dimension 6. So it's something which, it has been seen in other problems. But I would say that at the beginning for us, it was a bit surprising, right? So we were really sure we could do it. At some moment, I remember when Federico will say, oh, we cannot close this inequality at exact dimension up to 5. And then after trying a lot, we say, maybe it's false. Why don't we try to build a counterexample? And then we managed to build a counterexample, at least that was showing, okay, one has to do something different, actually. And these powers are optimal. So in their proof, also it was, I didn't say this is Deng, Sung, and Wei in 22. And both these are optimal. So the square root of log is optimal, and the n plus 2 to n minus 2 is optimal.
So it looks like that power would like to be
bigger than 1 for n equal 5, but you cannot because you cannot get an inequality which is better than linear, right?
Right, yeah.
Right, I mean, kind of the.
Yeah, for n equal 5, you will get something.
Yeah, because for n equal 6, that is exactly 1.
One.
Right?
Yeah, this
It's
is-
based by 1.
Exactly, so this only works in dimension 7 size.
Uh-huh.
Yeah, because in some sense, then, so
And then you cannot.
when you do the estimates, you have terms that compete, and this is the worst term in dimension 7. And then in lower dimension, you will have, it would be a better, the terms that you're looking at will be better, but there are still linear terms that you
cannot avoid.
that you cannot avoid, and then you get the limit, right? So, and this is really due to the interactions of these bubbles. So it's all this comes when you start to understand the error that you get when you look at this minus this. And you look at how much they interact, different bubbles, their behavior, this kind of errors that you get. The size of these errors is dimension dependent. And then it has just a transition, phase transition in dimension 6. Maybe just one application that I wanted to mention because I think it's also connects to the problem. This is what we showed in this paper with Ciraulo and Francesco Maggi. Was the following. So how can you, so you could say this is a nice problem, but why do you care, right? I mean, looks too much, right? But there are, for instance, very natural equations like the Yamabe flow. So these are flows coming from geometry analysis that you can rewrite as of the following way. dtu equal Laplacian of u plus u to the p. Okay. And now the idea, which looks very unusual, is to say, let me look at this parabolic equation as an elliptic equation with a reminder. This is my reminder. Okay, and I would like then to use, so the idea is that every time, if this is small, then I could apply that theorem and say that when this is small, which is when this is small, I'm very close to one bubble. And this is not crazy because when you have parabolic equation of this kind, you can prove like you can differentiate some, I will not do it, but times some energy values. And this energy will be something like the minus of dtu squared, weighted with u to a power alpha, let's say something like this. So you can get like what are called dissipations inequality. So which tells you that there is a quantity which is decreasing in time during this equation, and the dissipation is measured exactly by the dtu, but dtu is exactly this. So it means when you integrate this in times, it means that you have an energy, u at time 0, which controls the integral from 0 to infinity of the integral of dtu squared alpha, which means that for most times, this quantity should be small. And how small is this quantity? Well, this is small, then this is small, then I can apply these theorems. And in fact, you can apply this. And what we did in our paper was to prove that if you have this equation, then the solution will stabilize around the steady state, the minimizer. So this you prove that, let's say, u converge to u lambda z exponentially fast. Fast in time. You can give a proof of this result. There were other methods, for instance, developed by Simon Brendo to prove this kind of results. But then if you apply this kind of estimates, it just comes very, very quickly. You get like a Gromov estimate, which closes very quickly. So there are, every time you have a dissipation, this goes very nicely. There is one more thing just to close a bit to the picture, and I still have a few minutes. So I wanted to motivate this because this is the case where, so I wanted to present this because this is the case where we have a complete picture, but you could ask the same question I've asked here, so from Sobolev to critical point, for the isoperimetric inequality. So this is still a beautiful problem. And since we have spoken so much about it, I think it's worth mentioning it. So remember, isoperimetric inequality is what my function I have f of e, let's say volume equal to 1, which was perimeter of e minus perimeter of p1. This is my function. What is a critical point here? So if you take a minimizer of the perimeter and you perturb it, so you do your minimizer, but we know that they are both, right? But let's say I didn't know. So I have my E, and I know that it's a critical point of this. What does it mean? It means that if I take my E and I perturb it smoothly, so I have E epsilon, and I do d over d epsilon of f of E epsilon, and epsilon equals 0. And you know this is 0 for every epsilon, for every test function, for every variation. Then you discover that the mean curvature of your boundary should be constant. Okay, so critical point of the perimeter are sets with constant mean curvature. And then there is a famous theorem of Alexandrov. Which says the following, that if you give me a smooth set, the inner and smooth, bounded, and the mean curvature of the boundary is equal to a constant, then, and connected, then E is a ball. Right? Which is exactly the parallel with Sobolev. For Sobolev, you solve the PDE, the positive solution of the PDE, it's the bubble, is the minimizer. For the isoperimetric inequality, the only compact, smooth connected surfaces which bound a set are balls. Okay, but then you could ask the same question. A set which has almost constant mean curvature, is it true that it's close to a ball?
But if E is not smooth, can this be true?
It depends in which sense, but yeah, I would say if right now there is a theorem that says that if you have E sets of finite perimeter, where the mean curvature in the sense of distribution is constant, then it's a ball. So it's known, let's say, up to sets of finite perimeter. And then you could ask, okay, question, E is smooth and connected. Mean curvature of E is like constant plus little of 1. What can I say? Is it true or ball? And the answer is no, for the very same reason as before, because what you can always do is to take a ball, take another ball, and then connect them with a very small neck. And you can find the neck so that it's close in very high topology. So the mean curvature of the neck can be done so that the mean curvature is extremely close to a constant everywhere. So you can even do it very well, these necks. And you can do as many as you want, actually. So again, you have the same problem. I could start to take a lot of balls and do them together. And so here the analog would be, is it true that if I have this plus some bound on the number of balls, then I have to be close to the finite number of balls? The answer is yes, but there is no sharp result so far. So there are many results with different powers, different norms. Also here in which sense you are close. So for instance, there have been many results where the mean curvature is close to a constant in an infinity. This is a measure. But let's say if you have in mind this analog, the PDE analog, you would think that you would like to put as a norm there the dissipation of the mean curvature flow. And so really the right norm, I think it should be the mean curvature minus a constant in L2. And with L2 is essentially totally open because doesn't control anything. There is no regularity for minute surface at this scale. It's a bit of a disaster. Maybe in dimension 3 you are borderline, but let's say dimension higher than 3, it's a total disaster. So there are partial results with non-Nokia exponents, for instance, Ciraulo Maggi and Maggi with Neumayer and also a few others. So Maggi worked a lot on it, and he has a lot of partial results. But I'd say there is still not a conclusive result with sharp norm and sharp powers at this level. Okay, so now I think the time is over. I will stop here. Thank you.
Are there any questions? do you measure the number of poles in this context that are related to the?
Well, you block the volume, right? Somewhere. So you block the energy. So let's say, I don't know, either you, okay, you have to block two parameters. So let's say, if you choose, so you always rescale your set to choose this constant. So if you normalize, so let's say that the mean curvature of the ball is n-1, and then you can put here n-1, and then you put a sample plus, let's say that the perimeter of E is bounded by L plus 1/2 the perimeter of B1. And then so you have to block the perimeter after you block, let's say, the mean curvature. That's the kind of assumption. But even with one bubble, so even if you put L equal 1, there is still not a sharp result with this norm. So here is not even the case of bubbling the problem. We still don't know how to use the mean curvature to prove sharp stability. And it's actually, yeah, it's a difficult quantity to control.
Is there something for crystals?
At this level,
Qualitative.
so if the anisotropy mean curvature, then you are almost a wolf shape, right?
Right, exactly. And I mean, especially interesting if it is like, the crystal, the one with kind of, piecewise affine, right? I mean, that would,
Yeah.
sounds
No.
even somebody in mathematical physics might have asked the question. Yeah.
Yeah, so if your perimeter is crystalline, it's extremely difficult even to give a good meaning to this mean curvature, right?
Yeah.
It's very singular. But there is an interesting different question that you could have asked, which is the stability of the superperimetric inequality for crystals. So what I proved in what I presented for the isoperimetric inequality was the stability result. Erase this, right? For the isoperimetric inequality, I presented this inequality which says that f of E square root controls E delta B1. And I told you could do this for general perimeters. So you could have, your ball could become a convex set, the wolf shape. And then this would be an energy depending on kappa. So this would be like the anisotropic perimeter of your cell. And now this is true for every kappa. So our theorem gives a constant independent of kappa for every kappa. But you could ask yourself, if kappa is a crystal, can I hope to do something better? Because crystals are more rigid than balls. And the answer is yes. And that's what I proved with Zhang a couple of years ago. Is the following. So if kappa, let me give you an example. If kappa is like a square, okay, then, okay, let me just give you the application that. So why do you care about this stability result? You could try to ask yourself, okay, look at minimizers of the following energy: perimeter of E, or an isotropic perimeter of E, plus some potential terms. Okay, so I minimize energy, perimeter plus potential. And let's say that I put an epsilon in front, because you can always put an epsilon if you assume the mass to be small. So small epsilon is like, say, small mass up to scaling. So let's say I try to understand the perturbative situation of the perimeter, where I have a small potential active on my system. What can I say about the minimizer? If you apply these theorems, you immediately know that minimizers will be very close to the optimal guy. But then you could ask yourself, what happens in the case of crystals for the minimizers of this? So if I have the classical perimeter, the minimizer is a sphere. And if I put a potential, I could deform the sphere to let's say, an ellipsoid, for instance, which is very close to a sphere. Instead, let's say that kappa was this, in dimension 2, but in every dimension it's true, no? Then the minimizer, let me call it kappa epsilon, will be something like this. So if the minimizer for epsilon equals 0 is a square, the minimizer for this is going to be a rectangle with that parallel to the square.
There's not going to be any curvature.
Not only there is no curvature, the sides cannot even the angles are all the same. And this is true in every dimension. So you give me the minimizer, which could be any polyhedron. The only thing that can happen for normalized time is that you move a bit the phases parallel to the original one, but nothing else can happen. For the minimizer, this problem independent of G. A potential cannot break the crystalline structure at mole energy, which I think is rather cool.
Can you understand that? Because the PDE sort of has a Dirac mass sitting on these corners somewhat. So like,
I don't know if I can.
it doesn't look like you can, like, force it to become regular. Like,
Yeah, but you could have expected maybe.
but oh yeah, you could have expected that it turns though. Yeah.
It doesn't. So if this is the square, the angles are still totally parallel over them. How we prove it is that we prove a stability result for the isoperimetric perimeter of different sort, and we prove in fact that the energy of this kind of energy pickup of E becomes extremely. So if you take a minimizer and you start just to move the sides, the energy will vary smoothly. So let's say the perimeter of this guy is very close to the perimeter of this one. But the moment you tilt, the perimeter goes very, very fast. That's the intuition in 2 dimension. Now in n dimension, it's a bit more complicated. But in 2 dimension, actually the proof is like alpha page of this fact. The problem was to do it in higher dimension. So there are a lot of interesting phenomena, but I never exploit or understand how to use the mean curvature, because I don't even know how to write it for that energy.
Any other questions?
Yeah.
So once you go away from this case here, this other kind of theorem, then we go to the situation you were describing. Is there still a connection with the critical points of the isoperimetric inequality? Kind of my intuition is that there should be critical points of the isoperimetric inequality which do not satisfy this. At least in the convex case, this is true, but I'm only thinking about convex perturbations. So.
Sorry, say again, what do you mean?
So we can just add something about mean curvature, right? So then we can define mean curvature however we want to, we can ask this question. But the question came from understanding the critical points of the deficit in the.
Yeah, the isoperimetric.
Exactly. So could there be critical points of the deficit and isoperimetric inequality in a certain sense that do not give you, that are not false? You just lose the connection with this notion, particular notion of mean curvature that you.
But how? Because critical points of the isoperimetric inequality are constant mean curvature.
This is true even for non-smooth bodies.
Right. If you give me a set of finite perimeter,
Any set of finite perimeter,
then you can define a distributional mean curvature.
yes,
So you can define the mean curvature is defined through first variation.
yes.
Then you assuming the first variation to be 0, it exactly means constant distribution of mean curvature. It's an if and not if, because essentially this is defined through this formula more or less. And then it's a theorem that constant critical points of this are only bolts. So there is no other set which satisfies that. So you cannot
The
use.
example I'm thinking about are convex perturbations, which is completely different. I'm looking at a much smaller class of perturbation, right? So.
But if you have convex and mean curvature, then it's easier, right? Because then constant mean curvature on the convex sets implies that you have infinity in a second.
No.
Right? And then I can apply mean.
We'll discuss it later.
Any other questions? Thank you very much.